We're going to talk about capacitors, which are technologically one of the most important things from electrostatics and DC circuits. Recall the parallel plate capacitor, made of two parallel plates charged with the same magnitude of charge but opposite sign. So, for instance, we charge the top plate to plus Q and the bottom plate to minus Q. This is a weird. The bottom side of the top plate has charge plus Q. How come? Because all charge has to live on a surface, but the plus Q is going to be attracted to the negative Q here. We say that then the potential difference between those two plates we symbolize by V. And we're assuming at the moment that there's air or some other perfect insulator between them, so it can't just simply discharge across the way it would like to. Remember that the electric field lines look something like this, where they're mostly constant between the two plates, and there's some fringing on the outside, but it's mostly zero. Here you can say, like, this looks like a lot of field, but compared to the density here, it's very little. All right, a battery is a device that maintains a fixed potential difference between its terminals being the place where the charge can enter or leave. How does it do this? Magic, well, not really magic, but chemistry, stuff that we don't really talk about, the electrostatic arrangement of atoms in various metals and solutions that generally want there to be some charge separation, which we take an advantage of. For our purposes, batteries will be black boxes, and we will generally not talk about what generates the potential difference, just that it is being maintained by some chemical thing. We'll see later that we use up some of that chemical potential, and batteries will eventually run out, and we'll talk about why, but later in the class. If we connect each plate of the capacitor to its own terminal of the battery, charge will flow onto the plates. The idea being that there's a higher potential here, and they will be, which means that positive charges are being essentially repelled from the top plate, and negative charges are being repelled from the bottom plate. And so the positive charges come out, they move across, and they start collecting on the nearer plate, if you want, on the positive plate, the plate connected to the positive terminal. Likewise, the negatives move through here and go around here. Here we have something called a switch, which I'm sure you're familiar with. When the switch is open, there's no conducting path, nothing happens. When the switch is closed, it's a perfect conductor, and the negative charge can flow through that branch. One model people have is so-called charge escalator, the idea that the battery takes, in this case, positive charges and through the magic of chemistry, moves them from a place of low potential to a place of high potential. Notice, of course, they don't really want to go this way. They'd like to stay close to the negatives, but there will be some chemical magic going on to make sure that they are, in fact, maintained separate from each other. If there's nothing connected to the battery, then we build up positive charges up here and negative charges down here, and there's just a potential difference, but when we connect it to a place for the charge to flow, it does. And we see the positive charges will move out and start accumulating on this plate, and then negative charges will move out this way. Or you can think of it this way, that the positive charges come here, and then these positive charges repel any positive charges that were in the originally neutral plate. So those positive charges move in and try and get to this location, leaving negative charges on the other plate. But when the voltage across the capacitor equals the voltage on the battery, then there'll be a positive charge on the terminal here wants to go this way to get to flow away from the positives that is nearby, but it can't flow onto here because all these positives are pushing this way, and so when those voltages are equal, the current stops and the capacitor is considered to be fully charged. Notice here sometimes we use delta VC, sometimes we use just V. No big deal. As usual, we can think of potential as the equivalent to pressure. If we imagine this being some flow of fluids, then the potential acts like the pressure, and what we're getting here is that at one point when the pressure coming off this plate equals the pressure coming off that terminal, then there's dynamic equilibrium and everything just stops moving. So we get a steady state condition where the plates have the same potential as the battery. The peculiar symmetry of the parallel plate capacitor allows us to find a simple relationship between the voltage V and the charge Q that it stores. We know that the voltage is, of course, just going to be integral E dot ds, but we can just say ED here because we know that the electric field is constant, so it comes outside the integral. And then we know the electric field from Gauss's law is sigma over epsilon naught. And, of course, sigma is just the surface charge density, so it's the total charge over the area, which we see ends up over there. So we just combine it. We say that V is ED. Let's move E over to here. So V is QD over epsilon naught A. And then invert it to get that the charge is epsilon naught A over D times V. So far, it's just an algebra game. We then define the capacitance C such that the charge is the capacitance times the voltage. The idea of capacitance is what is the capacity of this parallel plate capacitor to hold charge? How much charge can it hold as we apply different voltages to it? And if it has a large capacity, it means that the voltage produces a lot of charge that resides on the capacitor. If the capacitance is low, then only a little bit of charge for a given voltage. The units of capacitance is the farad, named after Michael Faraday and symbolized by the letter F, which is defined as 1 coulomb per volt. But it turns out that 1 farad is a huge capacitance, like way too big. A single volt would provide a full coulomb of charge, meaning if you were trying to hook up one of these things up to even like a standard D-cell battery, you'd get a coulomb of charge on the capacitance, which almost certainly causes it to break apart. So typical capacitors are measured in microfarads or sometimes even picofarads. Although we define this using parallel plate capacitors, it turns out that capacitance is a purely geometric feature whose equation depends on the geometry. It's always in the form epsilon times a length, though. So here we have, for instance, our other one was epsilon A over D, but A over D is a length. And it will have to be, for consistency, always be some length times epsilon naught. Let's take a little closer look at the form of the capacitance for the parallel plate capacitor. We found that the capacitance is going to be epsilon naught A over D. Let's see if these at least make some sense as to why we can store more charge at a given voltage in a large capacitor. Well, epsilon naught tells us how easily electricity threads the space in our universe. It really talks about how easily things are polarized, that the atoms and stuff stretch out in the electric field, and the larger epsilon, the more they would stretch out. That actually turns out to mean that it would reduce the electric field. That stretching in materials would create a counterfield that would reduce the total net field. So if epsilon naught is larger, repulsions will be less effective, which means that we can store more charge because as we pile them on that plate, they're less effective at pushing new charges off. You can't really change epsilon naught. It's a feature of our universe. It's a fundamental constant. So in one sense, it's silly to talk about that. But it's nice to see how it works there. And we will eventually see that while you can't change epsilon naught, that's just one particular value of something called epsilon. And there are ways we can change the epsilon value. So we'll come back to that in part C of Unit 12. All right, if A is larger, then the charges have more places to spread out. The larger the area, the further apart they can get on the plate, and therefore the less they're affecting each other, so the more you can cram on before they repulse back. So that makes kind of sense. If D is less, it gets a little weirder. Like, why does a smaller distance have this effect? But when D is lesser, then the positive and negative plates are closer. So the negative plate can sort of effectively pull some more charge onto the positive plate. Remember that we're sort of talking about, we're talking about something that looks like this, as we have some positive point and some negatives already on the plate. And then I try and bring in a new positive. My positives are trying to push it away. But the negatives are trying to pull it down. Now, they're further away, so they're less effect and so on. So we usually can put stuff on here. But if we make the whole apparatus smaller, now this positive charge is closer. And so it can be sort of glued in. It resists that repulsion from the positives a little bit more. So making D smaller would allow us to put more charge on the plate as well. And that's what comes out here. All right, what is the capacitance of these two electrodes? Well, capacitance is charge over voltage. So we see we have 4 nanocoulombs divided by 2 volts would be 2 nanofarads. A actually reasonably sized capacitance. Capacitor 1 comprises square plates of side S separated by a distance d. We do assume d is much smaller than S. Capacitor 2 has plates of twice the length, but are separated by twice the distance as well. What is the ratio of the capacitance 2 to capacitance 1? Remember, the capacitance is epsilon naught A over D. And so we say if we double S, we've made A go up by a factor of 4. We've doubled D as well. That ends up being 2 to 1. It's more capacitance, but not quite as much as we might imagine. A given capacitor stores charge Q when maintaining a voltage V. All of that charge is then transferred to a different capacitor with 3 times the capacitance. How does the voltage on a new capacitor compare to the original voltage? Well, we have Q equals CV. So if this has gone up by a factor of 3, this has to go down by a factor of 3. It's 1/3 as much. All right. You don't have to have parallel plate capacitors for a capacitor. It can be really any two conductors charged to the same but opposite amounts and separated with some differential, some potential difference. So we could talk about cylindrical capacitors. Consider 2 long coaxial cylinders of length L and radius A and B, where A is less than B, and they're both much less than length. The reason for the much less than the length is to ignore the fringing effects that happen at the caps. If you apply Gauss's law to this surface, so we say this red one, we know that inside this capacitor, the electric field is 0, and outside the combination, because of the shell theorems, it would also be 0. But between, there'll be an electric field which is given by Q enclosed over epsilon. All right, so if we pick a fixed distance r, E is fixed, and so we get E dot dA becomes just E dA, take the E outside the integral. And of course, the enclosed charge is just Q. The area of a cylinder, this is, remember, cross-section of a cylinder, we have 2 pi r times the length of the cylinder. And so the electric field is Q over 2 pi L times r. And that's good Gauss's law of practice if you didn't remember it. The voltage from point A to point B, from the inner radius to the outer radius, would be minus the integral of E dot ds along that path. So we just kind of do that. And we say well, minus from A to B, and then we put on our electric field. I've picked this way because, as a reminder, we have this thing and this thing, and we have the electric field is pointing radially outward, and I want to take my path ds and have it also be radially outward so that the dot product is just 1, or is really just their product, E dot EDS. So we have here E ds. And we pull out everything we can, so Q over 2 pi epsilon naught L all come outside. I have minus the integral from A to B of dr over r, which I can treat the r as a positive, so I can just take that's the natural log, and then natural log b minus natural log a is natural log b over a. So we get the nice thing. The voltage looks like it should. It's a charge over a distance. For a capacitor, though, remember, we had just picked in here that this was the positive plate and this is the negative plate, and I just integrated from the positive to the negative. That was my path, but we usually define the capacitance, we define the voltage as being how much higher the positive plate is. So I really had wanted to integrate this way, and the way I do that is just turn everybody around, and so I find that the voltage difference on this capacitor is Q over 2 pi epsilon naught L times the natural log B over A. At that point, the capacitance becomes easy. Q equals CV, so Q equals this junk. Hey, there's a Q on both sides, we'll get rid of it, and it must be that the capacitance is 2 pi epsilon naught times the fraction L over natural log B over A, once again pointing out geometric factor, units of length. And that's worth knowing. Should you memorize this capacitance? Probably not. I'm trying to remember if there's ever a question they've asked. I guess if you remember it, it's good. I think once or twice they've asked you to derive it on some of the older free responses. I don't think they've done that in a couple of years. So I don't know. Commit it to memory maybe. Better if you know where it came from. All right. Do a similar trick for concentric spheres. So sit down and do the same kind of thing. Figure out the electric field and then figure out the voltage and then figure out the capacitance. All right, we know from the shell theorems that the electric field is the same as the point charge Q. And again, positive charge at the center here, so the electric field is just Q over 4 pi epsilon r square. So the voltage from inside to outside would be minus A to B of E dot ds. Again, pick so that E dot ds has no extra sign in it. And we get really just this sort of stuff that comes along. Here's E, here's ds. Pull everything we can that's outside. Now it's only Q over 4 pi epsilon. And we have dr over r squared, but that's easy because that's minus 1 over r. There is a typo in this script because when we put the -1 over r, this is really a minus b, right? When we evaluate all of this stuff. Partly because I'm just trying to keep this minus sign out front because I know I'm going to negate it in a second. So this becomes -1 over b minus -1 over a. And you can see that that ends up being what I have written there. As before, we actually want the voltage from going the other direction, i.e. from the negative to the positive plate. So the voltage we want is minus the thing we just found. This minus sign cancels out the other minus sign, so we just have q over 4 pi epsilon out front times that difference, which is fine. For historical reasons, we tend to combine that and have q over 4 pi epsilon naught b minus a over ab. That's just the algebraic combination of those things. And so the capacitance, which is q over v, becomes q over all that stuff. And you can see why we divided that is to get something very nice down here, where you get the capacitance is 4 pi epsilon naught ab over ba, or b minus a. Again, should you memorize that? No, probably not. Easy enough to get, not that huge a deal. It does have an interesting feature, of course, which is saying, let's let b go to infinity, and that would give us an isolated conducting sphere. Right? And the capacitance of an isolated sphere is worth remembering, but it's easy. The potential of an isolated charged sphere is at the surface is 1 over 4 pi epsilon times q over the radius of the sphere. So we can invert that to get the charge. The charge would have to be 4 pi epsilon naught r times v, which means the capacitance has to be 4 pi epsilon naught r. So we get that the capacitance here is just proportional to the radius. By the way, this is what justified the stuff we did early on in electrostatics, where we said that spheres will share charges according to their radii, because we know that now we can say, oh, well, if we have two spheres and they're of different radii, and we connect them with a wire, they become an equipotential. So they have the same voltage, so the charge will be the capacitance times that voltage. And so since the voltage is proportional to R, the charge will be proportional to R as well. And at least that justifies that sort of in retrospect.